Today on Breaking Point.
Random metal pieces.
We take for granted that the structures and materials all around us will be strong enough to withstand the forces and stresses of nature.
But how do we know how much force a material can actually take?
Well, we're about to find out. Hi, I'm Misha Leybovich.
And I'm Jordan Peck.
And we're the Bash Brothers!
Here for Breaking Point.
Today we're at the MIT Solid Mechanics and Materials Laboratory.
Down the hallway, they spend a lot of money, a lot of time, making new materials for all sorts of different applications.
But after they make them, we break them! Let's go have a look inside. Check it out. We're gonna be the Bash Brothers. Seriously, you're gonna love it.
Now, we're not actually supposed to be going in here, but I got my friend's key, and we're gonna check it out.
Now this machine here is for testing very, very small materials, such as thin films.
Now, they have another machine over here, which is used for testing the different materials at different temperatures. So you've got an oven here. It's for bigger materials than the other one.
And this here is the Big Daddy.
What we've got here is an Instron tensile tester.
What we do is we take a piece of material, secure it between the hydraulic grips.
Then we go over to the computer, put in some information on how fast it should go and how much force.
And then we let her rip.
So I'm just going to reach into the cabinet here and pull out a random piece of material for us to test on.
Take it to the breaking point, Misha.
Jordan, I'm going to take you to the breaking point. There we go. Here we go.
Now what we've got here is what the material scientists call a dog bone. It has two wide parts on the sides, which is where the hydraulic grips hold.
And the skinny part in the middle, which is where the magic happens.
Today we're going to be talking about stress.
And strain.
So now you've seen all the equipment, let's talk some science. What we have here is our dog bone. And we apply force to each end.
Now these forces can be described with some very simple equations. The first is the stress equation, where the stress equals the force that you apply divided by the cross-sectional area of the material. Now when you apply force to a material, it generally stretches, and we have an equation for that too. It's called the strain equation, and that equals the change in length of the material over the initial length of the material. But what are we going to do with these two? Fortunately, we're in luck. There is an equation relating the stress and the strain by using something called the Young's modulus.
Now, the Young's modulus is a material property of whatever we're using. And when we do the test, we get a graph, which looks something like this. It has a linear region and then a curved region. The linear region is what uses this equation, and that's called the elastic region. This curved part is the plastic region, where most of the stretching happens. And then, right here, is the breaking point. But just before the breaking point, the material starts to neck.
Now, most people, when they hear the word necking, would think of it as something that two people who care about each other very much might engage in.
But I don't know anything about that, because I wear a calculator watch.
Hello?
Hey!
Now that we understand the science, it's time to lock and load our dog bone.
And give it a yank. Now that we have it in the hydraulic grips, it's starting to pull. And we have a clock here to show you how long it's taken.
As you can see, this is proceeding very excitingly.
Yep.
It's pulling. You know what? Let's do something here. Bloop!
Now it looks like a torture chamber.
Freedom! Bloop! Man, tell us where the money is.
I'll never tell. I won't tell the likes of you.
Man, the fix is in. Bloop! So here we see a noticeable neck forming.
Yep, you can see it on the top there. And remember, as the neck gets smaller, the pressure is going to be more focused.
It looks almost broken, but we see there's still a little bit of load left on the material. And there it's broken.
Let's check the computer printout. From the graph here, which is the results from our experiment, you can see this little linear area. That's the elastic region. After it, this kind of curved area, that's the plastic region. And you can kind of see that the elastic region was so small that it must have been a very weak piece of metal. Yet, it must have been soft because it has such a long plastic region.
Now this area here, where the load barely comes down, is necking. Now as you can see, this is our piece of metal. And right before it broke, the necking area was extremely thin. This means that the force is concentrated over an extremely small area, and thus the stress reached enormous proportions, and our piece of metal hit the breaking point.
All that we've been